So what I want to talk about in this lesson is the periodic table and what's known as electronic structure. So what we do in general, elements in the same group of the periodic table have a very similar outer electronic configuration, and with that they also have similar chemical properties as well. So what do we mean by that? If we have a look here, so these guys here, so lithium, sodium and potassium are all group 1 elements, and they're what's known as the alkali metals. So group 1 elements, and they're known as the alkali metals. Now if we have a look here at their structure, they all have a similar electronic structure in that if you look at the very outer shell, or the outer energy level, what you have is you have 1 electron in here in the outer energy level. And what this means is that these, so lithium, sodium and potassium, will have similar chemical properties, and they'll have a similar way at reacting as well. So if we take, for example, sodium, and we can draw like this a Lewis dot structure. So this is the outer electron. Basically what sodium wants to do is it wants to lose the electron. It wants to get rid of this outer electron so that it has a full outer shell, and it obeys what's known as the octet rule. So that's what we mean, so that we have a similar structure. If we have a look here, so here we have what are known as the halogens, so they're group 7. So we'll just look at it on the periodic table for 1 sec. So these are the group 1 elements. And then if we have a look then at, so these guys here, which are the halogens, fluorine, chlorine and bromine. These are these guys here, the group 7 elements. So what we can say with the group 7 elements is, again, they have a similar electronic structure. The outer energy level, or the outer shell, it has 7 electrons. So if we look at all of these, they all have 7 electrons. So if we take chlorine, for example, chlorine is going to have 1, 2, 3, 4, 5, 6 and 7. So it has 7 electrons, and what it basically wants to do is it's not going to get rid of all those electrons. What it wants to do is it wants to gain 1 electron so that its outer shell will be full. So that's what it wants to try and do. So again, fluorine, chlorine and bromine will have similar chemical properties, and this has got to do with the way the electrons are arranged within the structure of the atom. Now what will be different between these elements, so if we take group 1, and I'll just write this down here, so this is group 7. What will be different between these elements is that as we move down the group, and as we move down the group here, what happens is the atoms become more reactive. So, and sorry, that's not in the case of group 1. As you move down the group, the elements become more reactive. So what do we mean by that? Well, as we can see is when we say reactive in relation to group 1 elements, what we mean is that how easily it'll be able to give up this outer electron. So if we think for a minute, like what's acting on this outer electron to stop it from being given away? Well, okay, number 1 is within the nucleus you have a positive charge. So you have this nuclear force, which is what's known an effective nuclear force, and it's holding on to this outer electron. So the stronger this nuclear force is, the more tightly held this outer electron will be. So what affects the nuclear force? Well, depending on the number of proteins. So as the atomic number, or the number of proteins increases, this force gets bigger because you have more positive charge. And as a result of that, if the force gets bigger, it has a tighter hold on the electron. Now, what are some of the things that dampen down that hold that the nuclear force has on the outer electron? Well, you have what's called a screening effect. So the more, if we have a look, as we move across here, we can see here that we get an increase, or more and more inner electrons. You have more and more occupied energy levels between the nuclear force and the outer electron. So as a result of that, if we take lithium, the outer electron in lithium is going to feel the pull much stronger because there's only like 1 energy level with 2 electrons between it and the outer electron. So it's going to have lithium will have a much tighter hold on its outer electron, and as a result of that, it's not as reactive. Okay, because it can hold on to this electron. It is reactive, it will give away the electron, but it takes a little bit more energy to pull this electron off because it's so close to the nucleus, and that nucleus has such a strong pull on it. As we move across here, so we see as these energy levels, these full energy levels increase, and the radius of, let's say, the distance between the outer electron and the nucleus, as that increases, and as this expands, this force that's acting on, that's holding this electron in place, it actually reduces. And as a result of that, it's just a little bit more easier to pull this electron off. So as a result of that, what's going to happen is as the radius of the atom increases, this outer electron is getting pushed further and further away from the nucleus, and therefore it's getting pushed further, it's not being held on as tightly. So it's much easier to pull this electron off from potassium, for example, than it is to pull the electron off, this outer electron from lithium, because if you look at the distance, there's a lot more screening or blocking, if you like, going on. The electrons are negatively charged, so they're actually dampening down the effect of the pull from the nucleus, and as a result, this is kind of more loosely bound, if you like, and it'll be pulled away. So the effect that has is, as you move down a group, there's an increase in the screening effect, as in you get more and more electrons in between the nucleus and the outer electron, and also there's a reduction in the nuclear force, as in the force that is felt by this outer electron decreases because it's been absorbed by all of these other electrons in here. And as a result of that, what that means is that the reactivity, or the ability for the atoms to give away this outer electron, increases, so they actually get more reactive. So as you move down this group, the elements become more and more and more reactive. Now, if we think about the group 7 elements, the opposite kind of thing happens. As you move down the group, the reactivity decreases. So what is it that, so what are these group 7 elements trying to do? They're trying to attract an electron to their outer shell so that they'll have 8 electrons. These ones are trying to get rid of an outer electron. These group 7 elements are trying to attract an electron there. So what do they use to attract the electron? Well, it's going to be the nuclear force, the positive force. So it's going to keep these outer electrons in place, but it's also going to attract an electron from another atom, for example, in here into its energy level. But what's going to increase that is the smaller, so the bigger this nuclear charge and the smaller number of electrons, let's say between the nuclear charge and the outside of the electron, the smaller that is, the bigger the effect, or the bigger the pulling power is going to be. So as a result, if we take fluorine, for example, any atom that comes into contact with fluorine outside here, it's going to feel a much stronger pull on its electrons from the fluorine nucleus than, for example, if you take bromine, for example. So if bromine comes into contact with some elements, some atoms, there's going to be a pull. This positive nuclear effect or force is going to be pulling on the electrons, but it's not going to be as strong because you have all of these layers of electrons between it and its outside. And as a result of that, the pulling power, if you like, is going to be dramatically reduced as well. So what happens is you get the opposite effect. So with group 7 elements, as you move down the group, and you get, so the radius of the atoms increases, the actual pulling power or the reactivity of the elements that are within that group actually decreases. So if we take like fluorine, for example, would be more reactive than bromine. Or another way to think about it is bromine would be less reactive than fluorine. If we look in group 1s, it's the opposite. Lithium is less reactive than potassium. Potassium is much more reactive. So if we kind of look at this, like let's say, so if we look at a very common reaction, so if you take, for example, so if you take sodium, Na plus chlorine, that gives you NaCl. So sodium, so we've sodium here, and chlorine, when they come into contact with each other, you get this, what's known as sodium chloride, or just basically common table salt. So what's actually happening here? Well, if we look at it from an electronic structure point of view, so you have sodium, maybe I'll do it up here. So you have, let's just get rid of these two for the time being, so we have a bit more space to work. So if we look at what's happening here, so if we take sodium, for example, and we just do this Lewis, what's known as a Lewis dot structure. So you have sodium. Imagine this is the outer electron for sodium. And then you have chlorine, and it has 8 electrons. 1, 2, 3, 4, 5, 6, 7. Okay, it's 7 electrons, it wants to get 8. So what happens is these react like so, and you get sodium, and then you get, so this will be positively charged, and then you get chlorine, and it looks something like this. And this is negatively charged. And what happens is this forms an ionic bond. These two ions hold each other together. But if we think about what's happening here with this, and if we look at this and we kind of break it down, so imagine you have sodium and then you have chlorine. So what's going to happen is, if we think about sodium, so this is kind of like what it looks like. It wants to get rid of this outer electron, and because there's, so for example, what's keeping this electron in place is the force that's coming from the nucleus. Okay, but what's actually repelling this electron and pushing it away are the repulsion of these electrons here that's in between the nucleus. Remember, these are all negatively charged, so therefore they're going to be kind of pushing it away, this outer electron, and the nucleus is positively charged, so it's going to be kind of pulling it in. Now what's going to happen is, when it comes into contact with chlorine, for example, so chlorine is going to, so the nucleus, let's say within chlorine, is going to exert a force on this outer electron. And as a result, so the pulling force by chlorine is going to try and pull off this electron, and the screening force by these electrons are going to kind of be pushing it away. So what's going to happen is, chlorine is going to exert a much more stronger pull. The nucleus of chlorine is going to have a much stronger pull than the nucleus of sodium, because there's more protons within it, and as a result of that, it's going to pull this electron off. So what's going to happen is it will pull this electron off, and this electron will form part of here. So then what's going to happen is you end up then with 2, so you end up with Na, and because now you have more positive charge than you have negative charge, this is going to become a positively charged ion. And with chlorine, what will happen is, because chlorine has gained all of these electrons, so it now has 8 electrons. So it has one more negative charge than it has positive charge, so it becomes negatively charged. So it becomes negatively charged. So what happens then as a result of this, you get this negatively charged ion of chlorine. So you get this negatively charged ion. And then these two attract each other, and you get what's known as an ionic bond, and they hold each other together. But if you think about like what's driving this, well, what's driving this is number one, the arrangement of the electrons. So because group 1 elements have 1 electron in the outer energy level, and group 7 electrons have 7 electrons in the outer energy level, these two kind of, they react perfectly with each other, or they complement each other. So if we think about this then as well, so if let's say if we were to use, so fluorine, for example, is going to be more reactive than chlorine. So fluorine is going to be, if you react fluorine and sodium, for example, you'll get the same kind of reaction that happens here, but it'll happen much stronger. So you end up with sodium fluoride, NaF, or sodium fluoride. So F is the chemical symbol for, sorry, F is the chemical symbol for fluorine, and sodium is Na. So what's going to happen here is, if you react, so for example, if fluorine comes into contact with sodium, it's going to have a much stronger, it's going to pull off this electron much easier than chlorine. And the reason being is because the nuclear force that's being exerted by fluorine is much stronger than on sodium, is going to be much stronger than the nuclear force of chlorine acting on sodium. The reason being is that if we think about, so the positive attractive force that's coming from the nucleus, it's not being absorbed by as many electrons. There isn't as many layers, let's say, between it and the outside. Whereas if you think of chlorine, you have these two layers of electrons here before, and so the force that's acting out here is going to be less. So as a result of that, fluorine is going to be much more reactive than chlorine, and it's going to have a much stronger reaction with sodium than chlorine. Now, another way to kind of look at it then as well on the periodic table, if we think about, so as you move across the periodic table, what's happening is, so if we take, for example, like lithium and sodium, it's much easier for these atoms to lose electrons because of the screening effect, and then also as well because of the nuclear force isn't as strong. But as you start moving across the periodic table, this number, the atomic number, actually starts to increase. So as you move across here, and as the atomic number increases, what happens is these elements are less likely to lose electrons. So if we, like over here, this side, these guys want to lose electrons. As we move across over here, these guys, it's harder for them to lose electrons. They want to actually gain electrons, or they want to take electrons off other elements. So if we think about, like, as the example we've seen here, so lithium, sodium, these guys just want to lose electrons. But these guys, which are on the other side of the periodic table, it's harder for them to lose electrons because there's a much stronger force acting on them in here. It's keeping them all in place. And as a result of that, what happens is the kind of reactivity that happens as you move, let's say, from left to right across the periodic table, they tend to gain electrons or want to pull electrons towards them. And what also starts to happen is, as you move across the periodic table, because these guys over here on this side, they have a much stronger pull on their outer electrons, the radius of the atoms tend to decrease as well. So the radius decreases. So if we have a look here, for example, so this is just the periodic table, but we're just looking at it in relation to the atomic radius. So what we can see here is, as we move left to right across the periodic table, the actual radius of the atoms decreases. And the reason the radius of the atoms decrease is because of the strong, as you go across here, the atomic number actually starts to increase. So the effective nuclear charge that's pulling the outer electrons in towards it increases. So as a result of that, the electrons are pulled in more tightly to the atoms. And as a result of that, the radius actually, the size or the radius of the atom actually decreases as well. So we can see this as we move across, just in relation to their atomic radius, it actually decreases as you move from left to right. So this is kind of like what it looks like. So, and as we can see, like if we have a look, so these are the group 1 elements that we're looking at here. So these group 1 elements, which are these guys here. So what we can see is, as you get more and more electrons and you get more of a screening effect, the radius increases, and as a result, in relation to group 1 elements, it's easier to pull off this outer electron, so the reactivity also increases as well. So as you move down the group like this, so as these radii start to get bigger and bigger and bigger, it's easier to pull the outer electrons off these. So as a result of that, they're much more reactive, and that's why as you move down the group, they become much more reactive because they want to lose electrons. Whereas if you think of fluorine, bromine, the opposite starts to happen. So these guys here, in order for them to be reactive, what they want to do is they have to use their nuclear force to pull off electrons from other atoms. So what they want is a small radius. So they want the nuclear force closer to their outside so that it can have a much stronger effect on atoms that are in its neighborhood. So the opposite starts to happen. So if you take, for example, fluorine, chlorine, and these guys here, the ones with the smaller, so fluorine, for example, is the most reactive. And as you move down here, and you have, for example, bromine and iodine, they are the least reactive because the nuclear force it's being screened by the electrons that are on the outside. And as a result, the opposite happens. As you move down the group, the elements within this group become less reactive. So that's just really, just looking at, just trying to tie in the configuration of the electrons and linking that in then with their reactivity, and also kind of taking into account the screening effect that we've talked about, and also the effective nuclear effect that you're getting from the nucleus as well, and how reactions happen, chemical reactions happen because of these outer electrons, which we call the valence electrons. And then it's just looking at the different properties as we move across or down groups. So hopefully that makes sense, and thank you for listening.